Okay, so let's get started. So we are now on lecture 20 and I have 10 more slots till May 20th or thereabouts, and that's when I plan to end. And I think covering the material, as far as covering the desired material, I think it's gone pretty smoothly, in the sense we are today going to discuss again geodesic focusing in the time-like case, and either today or more likely tomorrow we'll finish that and then start on the null case. The null case is more significantly more difficult and will take the double the amount of time probably, and then we'll still have 3 or 4 lectures to talk about, and by case I mean singularity theorem included. Then we'll have 2 or 3 lectures to talk about thermodynamics, black hole thermodynamics, and that will be it. Okay. So last time I gave a sort of informal discussion of focal points for geodesics, and we talked about it in the context of synchronous coordinates, which is a special coordinate choice. And some of the claims there were made in words. So today I'll try to do a more rigorous covariant version. So geodesic focusing. So covariant description. The original sources on this are Hawking and Ellis's book and then Wald's book. And so what we are going to do this time, where did I end last time? I discussed focusing in synchronous coordinates. Did I talk about Jacobi vectors last time? Okay. Well, if no one remembers, then I can do it again, because I don't remember. So the idea was to define focal point without having a pair of geodesics that meet. So earlier we drew diagrams like this. Here was P, here was Q. This was one geodesic, this was another geodesic, and then there was the story of that if these two, which start from a common point, also meet at a point, then we can continue to another point, and then the length of the original thing, which is locally a geodesic everywhere in the sense that it's parallel transported tangent to itself, is the same as the length on this other path. And then we know that we can sort of smooth out that path by doing this, and we'll gain some. In Euclidean case, this will be shorter, and in Lorentzian case, it will be longer because this is a time-like path. So this was an argument to say that when geodesics have focal points, then continuing after that, neither of them is a geodesic. Now we'll try to do this more precisely, and the nice thing is we'll only have one geodesic, one curve, which will sometimes specialize to be a geodesic, and there will be P and Q, and we'll describe things in terms of a single curve and some infinitesimal variations in terms of vector fields. So my practice will be to call a curve gamma if it's already a geodesic. Sometimes we'll have a curve which is not a geodesic, then I'll call it beta usually, and then it might become a geodesic with some conditions, but when I use gamma, it means it's already a geodesic. And P and Q lying on, I can just say gamma called focal or conjugate points. If there exists a Jacobi field, I think I wrote this last time, but anyway, a Jacobi vector all along gamma such that S mu equals 0 at P and Q, S mu not everywhere 0. Actually, even if S mu does have a 0, isolated 0 somewhere in between, then of course that point and the original point, or that point and the final point, will also be conjugate points. So we might as well assume that it's actually non-zero in between, and then the other case can be incorporated. Okay. So now we want to write some equations instead of using words to try and understand all the possibilities. And this I don't think I did yesterday. So we are going to introduce orthonormal frames, which we discussed very early in the course. So if you've forgotten, you should remind yourself EA mu. But we are going to do it in a little bit more clever way than if we just randomly introduced orthonormal frames in any manifold. What we'll do in this case is to choose A to be only going from 1 up to d minus 1. There won't be any E0. Okay. And what's the idea here? The idea is that the geodesic, being time-like, has already given us a time direction. It's simply the direction along the geodesic. So this only spans the frames in the transverse directions. Okay. Now we don't. Now that's one thing already. Also, we should keep in mind. Therefore, hence A is a space-like index. That will be important when we need to prove some positivity results later. And we are also going to choose them. So first of all, they'll be orthogonal. These vectors are orthogonal to the tangent vector at the initial time. And then we'll parallel transport these frames along gamma so that they always point orthogonally to the tangent vector to gamma. So let's write out the equation which tells us that. So parallel transport, so you should think A is actually from the point of view of vector fields, A is a label and mu is the vector index. Okay, so it's a set of d minus 1 d component vector fields. Okay. Now once upon a time earlier in the course we discussed that there's an actual covariant derivative under which E is actually constant, which has two terms in it, the spin connection term and the affine connection term, one for each. But now we are going to use a different covariant derivative, which is the one that pretends it doesn't know anything about the A index. So this one is defined to be del nu E A mu minus gamma lambda mu nu E A lambda. Okay, so no spin connection term. And actually this is the covariant derivative that Wald uses. He doesn't use the other one that I mentioned. The other one that I mentioned, actually when it acts on E, it always sets it to 0. That's called the Feuerbach postulate. But this one doesn't automatically do that. But what we are going to do is to choose the frames so that this one is 0. Okay. And sorry, not just the this doesn't ensure that, sorry, slightly wrong. This by itself doesn't ensure that it's parallel transported along the geodesic. So it is this which we want. This is what we want to set to 0. The parallel transport along the geodesic covariantly with including a spin connection term, that is 0. So it's different from the Fjellbein postulate. So this equation implies the orthogonality G mu nu EA mu U nu equals 0 all along gamma. And there's one more thing it implies, which is also useful, which I'll come to in a minute. You see, when you have a congruence, then you have as you know, you have concepts of expansion, shear and rotation. And this will actually make sure that we don't have a congruence right now, by the way, we have just one geodesic. But around that, we want to make sure that the rotation, whatever is going to be rotation when we differentiate it, should be 0. Rotation, as you know, comes from first derivatives of the tangent vector, antisymmetric part. So that will also be set to 0, and I'll come to that in a minute. Okay. Now, now let's consider the Jacobi vector S and ask what is U mu del mu of S nu. So this is the same as S mu. So these are of course, here I don't have to put a bar. The bar is needed only if it acts on something which has a frame index A. Just to tell you that it's not acting on that. This equation is the fact that locally we can think of having a parameter tau, which is the proper time along our geodesic, the same geodesic from P to Q. And then if this is the proper time, then of course U, the vector, is del by del tau. And now we have a deviation coordinate S, and then S, the Jacobi vector, is del by del S. And because these are independent directions, they commute in these coordinates, and that commutation is the same as the Lie bracket is 0, which implies this thing. Now we remember that this gradient of V, we had given it the name B nu mu, if I remember right. Yeah. So therefore this is equal to B nu mu S. And this is the quantity, this should be U. This is the quantity whose trace and symmetric and antisymmetric give me the trace, then symmetric traceless and antisymmetric parts give me the expansion, the shear and the rotation. Maybe we should just write it since it's been a long time since we discussed it. So B mu mu is theta, B mu nu minus 1 by d minus 1 G mu nu. Theta is sigma, and B mu nu antisymmetrized, or this symmetrized, and B antisymmetrized is omega. Good. Okay. Now what can we say about this quantity? We can also write this for short as gradient in tau of S nu. And now we can use this to get an equation on the frame components. We want to refer everything to frames. So this one we already know is given by this, but we want to refer it to frames. So we'll write S as E what shall I do? Yes, E A mu S A. So the inverse of the standard relation, which tells me the frame component with respect to the general coordinate vector component. Now we notice that this covariant derivative, this is just short for u dot del. This covariant derivative can distribute on this and this, and there are two ways it can do that. Either I can treat this as the full, this is a full covariant derivative because what it's acting on has no A index, that's been contracted away. So it acts just thinking that its argument is a vector. But if I distribute it, I can distribute it as the full covariant derivative on this, which would give me 0, and then the covariant derivative on this, which would give me the spin connection term. But I can also distribute it as the barred covariant derivative on this, which doesn't act on the A index, and the ordinary derivative on this, because this doesn't have a vector index. So this is actually equal to del bar tau of EA mu SA plus EA nu dSA by deta. No connection here. This is an identity, very easy to prove. So there are two ways that I could have distributed it, and I am choosing the way which involves del bar acting on E. And since del bar E, the gradient bar on E has been chosen to be 0, it just gives me this. And now you can see why I am doing all of this. My formulae will be simple because I'll have differential equations which involve ordinary derivative rather than covariant derivative. So I can hope to integrate them. Okay. Now I can go back to the original equation. So therefore the equation covariant derivative in tau of S nu equals B nu mu S mu in frames turns into the simpler equation dSA by d tau is equal to BAB SB. So this is one thing we have benefited from using frames. And now I claim, I don't want to go into details of the proof, but I think if you are not, if you want to, you should look at it as an exercise. I claim that this BAB, which is our original B mu nu but referred to frames, has the property that omega AB, which is equal to B anti-symmetrized, is 0 by virtue of our choice of frames which are parallel transport. That will come in useful later on, so you just have to remember it. But this is the equation for S. Okay. Now let's write the geodesic deviation equation. After all, we are trying to understand focal points. For that, we need to understand the existence of a Jacobi vector which vanishes at the beginning and end of a curve. And geodesic deviation equation precisely tells me how Jacobi vectors behave because they solve that. And in that equation, I would give a boundary condition that the Jacobi vector vanishes at the beginning, which I can always do, and then I have to find the condition that it vanishes again somewhere else. Then I get conjugate points. Okay. So for the geodesic deviation equation, let's write it. Let's remind you what it was in the covariant form. It was this on S alpha was the Riemann tensor alpha mu rho u mu S2. And now, because of the manipulations I've shown you, you won't be surprised to find that in frame coordinates, it is ordinary d2 SA by d tau squared is equal to R A B C D U B U C S D. Simply all things are referred to frame coordinates. And as I said, it is very important that here these A, B, C, D run over only d minus 1 values. Okay. Now, this equation is a second order differential equation. So, it's determined by knowing S and ds by d tau at the initial point. The solution will be determined. So, let's assume, because we are looking for focal points, assume SA is equal to 0 at, I guess, tau equals 0. So, we will simply shift our proper time so that in this geodesic, well, most of my, maybe I don't know what I should do. I think I like to call these points tau 1 and tau 2, so that let's say tau equals tau 1, the initial point. My notes are a bit inconsistent, but I'll correct that. So if this is the case, then SA, first of all, what does S depend on? It depends on two coordinates, tau, which is the proper time, and this small s transverse coordinate, because I'm working with a one parameter family. SA therefore of tau and small s is equal to AAB of tau and s, SB of tau 1. So what have I said here? No, sorry, something. No, I wrote something wrong. Tau 1 and s. This is not right. ds by dt. Let me explain. I've chosen s to vanish at tau 1. Therefore, ds by dt, d tau cannot vanish, because if both vanish, then s just vanishes forever, and we have decided that it's not always vanishing. So, if this is 0, ds by d tau at tau 1 has to be non-zero, and since it's a linear equation for s, that means s at any value of tau is determined by this transformation acting on the initial value ds by d tau. That's all. So this matrix AAB contains the information about the time evolution of the Jacobi vector, and it is that matrix which we should study. Basically, you can see already from this that from this formulation that vanishing of S at any future tau is the same as this matrix having a zero eigenvalue. So when it develops a zero eigenvalue, that's when things will focus. Okay. And of course, A is invertible. That's pretty obvious that it should be. So now, question? Yeah.
Invertible and also a zero eigenvalue?
Right now, we don't need to. So, okay. So A vanishes at tau equals tau 1, because if I put tau 1 here and here, this vanishes, and this we have decided doesn't vanish, so this must have a zero eigenvalue at tau 1. Yeah, only at tau 1, and it should be non-singular after that. So let's say for tau 1 strictly less than tau, strictly less than tau 2. It will have a zero eigenvalue at both ends. So thank you, that's a more precise, correct statement. Okay. So now let's apply this in the, let's substitute this in the first order equation which we already wrote, which said that dSA by d tau is equal to BAB times SB. So I plug this into this. So on the left side, I get, therefore I get d by d tau of b. I'm just suppressing the s argument because it's there everywhere. So we'll just call it tau, and then dsb by d tau at tau 1. This is equal to BAB, then ABC of tau, and then SC of tau. So basically I have just inserted S equals A times ds dt initial into this equation and found that d by d tau of this quantity is BAB times S. And now let's expand it. So this is just a constant. So I get, sorry, something I did wrong.
DSC.
Yeah, this is d by d tau, and this is tau. So this is d by d tau of AAB times DSB by d tau at tau 1, and this is that. Now you see that there's a ds by d tau at tau 1 on both sides, and it's completely arbitrary. It's my initial condition. So I can cancel it, and whatever multiplies it has to still give me a true equation. So as a result, I have a differential equation for the matrix AAB. And the equation says that this is just BAB, ABC, and here is AC. Or maybe I prefer to write it this way. Anyway, there's one common index, and that. Just a matrix equation. And nicely you can just write this as if A was just a matrix with an underline symbol to show that it's the whole matrix, then this is matrix B times matrix A, and this tells me that B is A inverse dA by d tau. Wherever the inverse exists. Okay. Well, B, the matrix B is what we wanted exactly because its trace is the expansion, and we want to know what the expansion is doing. So that equation in turn says that trace of B is trace of A inverse dA by d tau, and that's what we call theta, the geodesic expansion. And so we get a nice expression for theta in terms of the A matrix. If you think back to what I did last time, we had a very similar expression in terms of a d minus 1 cross d minus 1 matrix, which was the spatial determinant Gij. It was theta was exactly trace of G inverse G dot. Okay, so we realized that in a covariant way, this A is encapsulating the same information as the d minus 1 cross d minus 1 matrix Gij in synchronous coordinates. But now we are not in synchronous coordinates, but we are in something very similar because we have chosen frames, d minus 1 frames, which don't have rotation and which are parallel transported. Good. So that's what I have to say about theta. Now, what about the geodesic deviation equation? Well, no surprise, that also comes out to be an ordinary differential equation for the matrix AAB. This is just equal to R A B C D U B U C A I have too many repeated indices. C D E U C U D A E P. So the equation, the geodesic equation has now become an equation, a geodesic deviation equation has become an equation for this A matrix. And now it's a matrix valued equation, so again we can, as before, it's second order and linear. So as before, we just need to know the matrix at the initial moment and its first derivative. But we know that the matrix vanishes at tau equals tau 1 because it's the one which tells me the Jacobi vector, and that vanishes at tau 1. So AAB at tau 1 is equal to 0. What about d by d tau of AAB? At tau 1, what should this be? Tell me. Well, you have to remember how A was defined. It was defined as the matrix which relates S at any time with ds by d tau at the initial time. So if I differentiate this matrix, this equation, I get dSA by d tau at any time is dAAB by d tau at an arbitrary time times dSB by d tau, but at the time tau 1. So now can you see what AAB at dA by d tau at tau 1 should be? Evaluate that equation at tau. That equation is true for arbitrary tau here, and this is tau 1. But I can choose this arbitrary tau also to be tau 1 and then 1. So this is just is equal to delta A. Good. Okay, and now supposing there is a time, suppose there is a focal point at tau 2. So tau 2 we have already chosen our curve, and tau 2 is just label sum. So tau 1 was the initial point where the Jacobi vector vanished, and we want to know if the Jacobi vector also vanishes at tau 2. So this can happen. So this means SA at tau 2 should be 0, and this implies that AB evaluated at tau 2 times the initial condition, just using this equation now, evaluated at tau equals tau 2. So dsB by d tau at tau 1 equals 0. And of course, this means AB has A0 eigenvalue. And this in turn means det A is 0 at tau. I should put an argument at tau 2. Okay. And if we are assuming that there is no focal point between tau 1 and tau 2, another way to say it is the first tau 2 should be the first place where we find a new focal point after starting at tau 1. We define tau 2 to be the very first time we find another focal point, so there is nothing in between. which is a focal point, and so det A should be non-zero in between, exactly as very early on we said that A is non-singular between tau 1 and tau 2. So far so good. Okay, so now with all this formalism set up nicely, we can use the Raychaudhuri equation and get some answers. And the answers won't be very surprising, and actually many expositions just leave it at whatever words I used last time. But I thought since this is the sort of course where we are doing things a little bit formally, let's try to continue doing them that way. So let's look at the Raychaudhuri equation. Time like one, we've derived it. We've derived it actually in the covariant form. Anyway, it doesn't matter which formalism you derive it in, it's the same equation. It's minus theta squared upon d minus 1 minus sigma squared. So we've chosen this to be this congruence of which this geodesic is one geodesic to be what is the word, hypersurface orthogonal. So there was no omega squared term, and then finally there's in the covariant form we write r rho sigma u rho u sigma. If u is identified in the coordinate where tau is a coordinate, then u is 1 0 0 0, and then this is r 0 0. Okay, good. Now we can relate this to the stress tensor, and if there's a cosmological constant, then that also, but we don't need to do any of that right now. We'll just keep working with this quantity and get some conditions and prove a couple of state and prove a couple of theorems. So good. So this theorem is I think originates in Hawking's work, and then it's explained also in Penrose. So let me write it. It looks a little formal, but it's saying something we sort of know, but it's a little bit more precise. Let P prime be a point on gamma in the future of P. I'll draw a picture. Here is P, here is Q, and P prime is somewhere there. In the future of P, and Q will come later. So in fact, we are going to identify that conditions under which there is a conjugate point Q after that. Okay, and suppose R rho sigma u rho u sigma is greater than or equal to 0 along the geodesic gamma. And now this is a bit scary because I am saying greater than or equal to 0. What if it's equal to 0? After all, what if R is 0? If R is everywhere 0, we certainly don't think they'll be focusing. So we are not going to get very far with that kind of assumption. But we add an assumption that the full Riemann tensor mu rho nu sigma mu u rho u sigma is greater than 0 at some point. In fact, at some point between P and P prime. Now we get two nice outputs. Then 1 theta, the expansion at P prime, is negative, and 2, there is a focal point Q on the geodesic in the future of P prime. So let me just make some comments about the statement, then we'll prove it. It's a bit of a long statement. In the more informal discussion of last time, we simply said that if theta is negative somewhere, there will be a focal point in the future. Then this was the if. Now we are not even assuming this is true. We are assuming something much weaker, which is that simply R00 or R component along the geodesic is not negative, and there is some point where the full curvature evaluated again along the geodesic is positive. Then we can predict that theta will be negative somewhere, and from that we can also predict there will be a focal point. So there's a double prediction. So for this, actually it's quite an amusing thing. For this we actually need to invoke the Raychaudhuri equation for the shear sigma, which we haven't used before and which actually I think I didn't write before. One thing you might remember, I'm not sure, did I write the Raychaudhuri equation for omega, the rotation? Okay, because actually you can write, there's an equation for all of them, theta, omega and sigma. Raychaudhuri's actual equation is for theta, the expansion, but there's an analog first order d by dt equation for omega and sigma. Now the one for omega has the nice feature that if I set omega, the rotation, to 0 initially, that equation preserves it. That is, d by dt of omega is proportional to omega or omega squared. So if it's set to 0, it will stay 0. That is not true for sigma, the shear. If you set the shear to sigma or to 0, we are going to see in a moment that with this condition, the shear will turn out to be non-zero after some time. Now, what are the terms on the right side of the Raychaudhuri equation? We have minus trace sigma squared, and we also have this Riemann term. So even if this term, this Ricci term, even if the Ricci term is not going to help us, it just insists on being 0, the shear term will help us to get a negative expansion. That's the idea. Now let's work it out. So let me write the, let me write the shear Raychaudhuri equation. As I said, he didn't write it down, but it just follows from the standard derivation. So this is equal to minus 2 by d minus 1 theta sigma mu nu, then minus sigma mu rho nu. Then there are some omega terms which just for completeness let's write it, minus omega mu rho nu plus h mu nu upon d minus 1 sigma mu oh sorry, I can't use mu, rho sigma minus omega. And now the interesting term, C sigma mu rho u sigma u rho, where C is the Weil tensor. And then there's another term, half h mu nu h mu sigma. It's a very long equation, this one, a bit tedious. Yeah, so these are all the terms in the Raychaudhuri equation for sigma. And though I won't write it here, I'll just mention that the one for omega doesn't have such a term. That's why omega, when you start it 0, it will remain 0. But sigma, supposing I start it to be 0, then all these first few terms just vanish. Omega, anyway, I'm setting 0. Sigma, I'm setting 0 only at the initial instant. Then only this and this are there later on. Okay. So now if we assume the worst case where R rho sigma is 0 along this, even then this term, I claim, is going to give me a negative contribution to the, is going to give me a, sorry, it doesn't matter what sign. The point is that this term will give me a non-zero contribution in d sigma d tau, and I don't care whether sigma is a matrix, it can have positive or negative values, but I'll be getting sigma squared on the right side of the Raychaudhuri equation. That's the important thing. So sigma mu even if initially 0, at tau 1 will become non-zero for some tau. Now, in principle, it looks like you could have some freak situation where the last two terms cancel, but I think that's not allowed, and I'm not sure at this moment what's the reason, but I think it should be easy to show that they actually can't cancel. Okay, and then we get the right side of the, so then we get theta dot plus theta squared by d minus 1 equals minus trace sigma squared and minus some r, right? This was the Raychaudhuri equation, and all we want to know now is the right side negative, and we've said that this is greater than or equal to 0 everywhere on the curve, and this, though it may be 0 in the beginning, at some time it's definitely negative. So at some time the whole thing is negative, and that's basically enough to tell me that the conditions of the theorem are satisfied, and the theorem says that there is a conjugate point. So this implies, so it's the same analysis as I did before. The only difference is that dot now is with respect to tau, and we've put some weaker conditions. So people like weaker conditions because if you have a theorem which you can prove with very weak conditions, then then you know more, because it might be that for some reason a very strong condition isn't actually satisfied in nature, but the weaker you make it, the more likely it is actually to be satisfied. Okay. So then conjugate point arises, and within finite proper time, and we worked out, I mean, the integration of this bound So this is less than 0. That's really all you need to work out the time. And the time I wrote, I think, in the statement of the theorem. Did I write it? I forgot. Tau 2 minus tau 1 less than d minus 1 over this value of theta and p prime. P prime is assumed to be the point by which theta has turned negative. Did I write this number in the statement of the theorem? I can't remember, but no? Okay. So the theorem says actually three things. One, that under those conditions theta is negative at some time. Two, that there's a focal point at some future time. And three, that that future time is not arbitrarily far away but is bounded like this. Okay. Now there's one sort of caveat which is important and must be mentioned here because finally that is what's going to happen. We have been assuming that we can go to large tau to reach the conjugate point. And this assumes that the geodesic is complete or inextendable. We once talked about what is an inextendable curve, and you can have a curve which is extendable, which actually means that it sort of ends abruptly for no good reason. And if my geodesic, for example, just ended abruptly, then obviously I can't go beyond it to find, supposing the conjugate point was going to happen 1 hour in the future and my geodesic ended 10 minutes from now, then I'll never reach that conjugate point. So when I say confidently that there must be a point tau 2, it's only under the condition that the geodesic is actually future inextendable. That should be remembered. Okay. So in fact, the one version of the statement is, if I put those two conditions, that r dot Ricci dot uu is greater than or equal to 0 and Riemann dot uu is non-zero at some point on a geodesic, then every complete geodesic has a pair of conjugate points. That's the correct statement. Okay. So yeah, as I said, we have not really done anything very new, but we have given a sort of formal look to the statement and been a little more precise. And now a nice theorem which will take about 10-15 minutes, I think, to prove, and we'll probably stop there. This theorem involves having a curve between 2 points called beta, which is not given to be a geodesic. Okay, but it's a smooth time-like curve. So we'll just assume it's smooth and of course time-like. And there's a theorem for it which says the following. Beta is a theorem. Beta will will maximize the proper time. Sorry, I should use it. Locally maximize. I'll explain what locally means. Locally does not mean for a small duration along beta. It means for a small deformation away from beta. There might be, imagine there's a length functional between p and q. In fact, we don't have to imagine it. It's nothing but the integral from p to q of the norm of the tangent vector. If the tangent vector is u, then square root of minus u dot u is the norm, and I integrate it. Now, if we don't know much about the manifold, it could be that this thing maximizes the proper time, but there's another one which goes like that, very far away from this, which even more maximizes the proper time. That is, the length function might have two maxima, one of which is more maximum than the other, but they are well separated. Okay, that I can't rule in or out, because I'm doing calculus near this curve. So obviously, if I'm only working to first or second or any finite derivative order, I'll never reach that far away point. That's what locally means, the proper time. Between P and Q. If and only if it is a geodesic with no focal points between P and Q. So this kind of finally completes the picture that I sketched for you last time. So there are several consequences to this. First of all, this guarantees that if I tell you beta is a geodesic and there's no focal point in between, that is the Jacobi vector, there's no vanishing Jacobi vector in between, which is also vanishing at this end or at that end, then automatically it maximizes the proper time between P and Q. If it's not a geodesic, it can't possibly maximize the proper time, if and only if. And even if it is a geodesic but with a focal point, then also it can't maximize the proper time. So that the only thing that can do the maximization is a geodesic with no focal points in between. Good. Okay. So now time to write a whole bunch of equations. They're quite simple, but the interpretation is a little subtle. So now we consider, here's the proof. Are there any questions, by the way? Please interrupt if people are more quiet than usual. Okay. So the proof goes like this. So for the proof, we imagine a smooth family, but very carefully we have to realize that we are not assuming it's a geodesic congruence. So smooth family of curves So it is a congruence of family of smooth curves. Actually, people write smooth family of smooth curves. It looks redundant. This one says that each curve is smooth, and this one says that the whole family is also smooth. And we are doing essentially the same thing we've done before with geodesic congruence, namely these curves have a parameter tau along them, and the family has a parameter small s transverse to it, except that we have nowhere said that any of these curves is a geodesic right now. But there is one curve we are interested in, beta, so that should be the one at the end of the family. So this is beta, then this is tau, this is the direction s, and then we have any smooth family of curves. And in this family, I can write the tangent vector to a curve as a function of tau and s. S will tell me which curve it's the tangent to, and tau will tell me at which point in proper time it's the tangent. Okay, such that u mu of tau and s equals 0 is tangent to beta, my original. So I've chosen this small s parameter such that when it vanishes, I'm on this. So this is the origin of that coordinate s. Okay. And even though this is not a geodesic congruence, as long as I have a smooth family with these properties, it is still true that I can think of u as del by del tau and s as del by del s, and the d bracket of u and s is 0. These equations still hold even in this more general family. Okay. Now I want to assume that this s deviation vector vanishes at the initial and final points, and then we have to consider we have to find the proof of the theorem. So we take S mu equals S mu at tau 1, at tau 1 for all s. So this family passes through P and Q, so I drew it badly. Like that. And so the deviation vector at tau 1 for any s is 0, and again it is so at tau 2 for any s. And what is the length of any curve? Now, length of course means proper time. I use the word length. Total proper time along any curve is obtained by integrating from tau 1 to tau 2 the function mod u in tau, where mod u is square root of minus u dot u. And since u is right now not the tangent to a geodesic, mod u is not a constant along the curve. That's the whole thing. We have to actually extremize it to get a geodesic. Now we are going to evaluate the change of this proper time. It's a bit complicated to give it a name. Wald calls it tau of s.
Which one?
This whole integral, the total proper time. People call it L, Z, various things. Maybe I should call it capital T. I don't think that's been used. Because this is not a local number, it's actually a function. And what is it a function of? It's a function of s, because s is what defines which trajectory, which path I'm on, and then t of s will be the proper time from P to Q of that path. Okay. Now we want to calculate dt by ds, and it's fairly simple but illuminating, and there are a few things we'll learn on the way. So if I want to vary in s, this integral is from tau 1 to tau 2, I can take d by ds inside that, since s and t are independent coordinates, and d by ds means the gradient along a directional gradient along the Jacobi vector capital S. So it's S mu d mu of mod u integrated d tau. So far so good. I'll call this index name. Now this involves a square root, so I can write this by taking this. So when I differentiate this, which is that square root, it's 1 upon twice of this times the derivative of u dot u with a minus sign, which will also give me a 2. So finally I will have minus integral 1 over mod u, then u mu s nu del nu u So minus u mu is what came out of that square root, and this is it. And now it's up to us to manipulate this into a useful form. So I believe we use the vanishing Lie bracket rule, which tells us that S del u is the same as u del S. So this is equal to minus integral 1 by u S mu, sorry, u is still there, then u nu del mu S mu. Yes, exactly. You just interchange the role of S and u in this thing. Integral is always over tau d tau, and it's from tau 1 to tau 2, so I won't keep writing that. And now I do an integration by parts. Not exactly by parts. Sorry?
The del mu S mu has an expression.
Del mu S mu has an expression.
And we can use that.
We can use that, but I think we don't want to use that now. What was the expression? Remind me. Not just del mu S mu, right? It's this thing you have said. Yeah, but that we don't want, that will come to later. Right now we are just going to manipulate this. So our goal actually is going to be to show, first of all, to find dt by ds, but also to show that if this vanishes, then the geodesic equation is satisfied, which I think I've already said quite a lot earlier in the course. But again, in this formal language, let's just do it. So I'm going to keep u nu out of things by writing integral u nu, and now this del mu I'll act on u mu over u. Del mu u mu over u, which is the unit vector, if you like, times S mu, and then that introduces an error which is minus del mu of u mu S mu over u. So here what I did was to just keep u nu fixed, and then it's this times that. So I acted with this on only that, which with a minus sign, to cancel that. And then I also have the term where this acts on this as well as this, which is that. But unfortunately I have, this is correct, my notes agree with this. There's an S missing, S mu, this is correct, all of these terms are correct. And one of these terms is a total derivative. Why? Because it is this one. This term is u nu del nu of something, but u nu del nu is d by d tau, and this is an integral in tau. So this term vanishes. Well, if I want to be, I should be more careful. This term then gets evaluated at the endpoints tau 2 and tau 1, but I know that S is given to vanish there. So therefore this term really doesn't contribute. Now, I didn't use any assumption about what S mu is. This is just an equation involving any arbitrary vector which is perpendicular to the geodesic. And therefore, this can only, so therefore this must, so therefore dt by ds being 0, if and only if this integral vanishes, but for arbitrary s, therefore this part of the integral must vanish, and this is u nu del nu, u mu upon mod u equals 0. And what is this equation? Can you guess?
Parallel transport of a unit vector along the
Yeah. So actually what it is the non-affinely parameterized geodesic equation. If you work this out, you will get u dot del on u over that, and then you'll get an extra term from differentiating that, but it will again be proportional to u. So in the end what you will get is the equation for a in general non-affinely parameterized geodesic. And when will it be affinely parameterized? When u is constant. Any constant will do. But we haven't assumed that. Okay, so we've shown that stationary total proper time leads to a non-affinely parameterized geodesic. Okay, good. But now comes the more interesting part. We would like to calculate the second derivative d2 tau t over ds squared of the proper time. So this is the second order deviation away from my curve beta. So, and remember, beta has been taken to be not a geodesic. Only if I impose this, then beta is proved to be a geodesic. And if beta is if given to be a geodesic, then of course this also must be true. Now I'll assume beta is a geodesic and calculate the second variation, but we'll encounter some subtlety here. So what is this? This is the integral tau 1 to tau 2. The second time I do this, I have to again dot with s lambda gradient lambda, whatever was there before. And what was there before was s mu u nu del nu u mu. Okay. Now I want to calculate this quantity and actually also this one at s equals 0, I should have said, because remember I used the vanishing of the Jacobi vector. That's only true at s equals 0. This also I want to calculate at s equals 0. Okay. Now, since I assume this to vanish, this is a geodesic which is not affinely parameterized, but once it is a geodesic, then I know that the length of its vector is constant, and therefore I can
even in this equation, if
yeah.
you expand the derivative,
Yeah.
One part will be u mu and there will be u mu, and it will be there will be modulus equal to constant.
Yeah, and therefore using that, therefore the equation now, once I assume this is 0, then this equation is equivalent to u. I can reparameterize u so that I get u dot del on u is 0. Automatically it's not 0. See, a non-affinely parameterized geodesic has a tangent vector which is actually changing its length as I travel. But as you know, we've done this calculation in detail, that you can just reparameterize it by a function, and once you do that, then the new u will be affinely parameterized, and therefore u del u will be 0 in the new parameterization. So let's assume, before we get on to the second derivative, assume that it has now been affinely parameterized. Once we know it's a geodesic, we are sure that it can be affinely parameterized, so we'll do it. Just to simplify our calculation. Actually, the calculation I'll do here works also if it's not affinely parameterized, but just lot of mod u's in the denominator that I need to keep differentiating. So now comes an interesting question. We know that u nu del nu u mu is 0. So does that make this 0 automatically? Yes or no? No, because this is going to differentiate it further. Okay, and in what direction? In the s direction, away from it. So I only know right now that my beta, original curve beta, is a geodesic. I do not know that the curve which I get by moving away from it is geodesic. So I can't set this to 0. Okay? Because I am going to first differentiate this factor and then set small s equals 0 to get back to beta, and then this is not, it's not true that this is 0. However, I can expand this thing. So I have s lambda. One term will be when this gradient acts on s mu, like this, and then this. And this term I can set to 0. Okay, where this only acts on this. Because now I evaluate all this at s equals 0, and that's why this is 0. Then there's a term where this acts on that. And that term is s lambda. And now there's a bit of calculation. S lambda, s mu. Let me just read it off from here. Then there will be del lambda u nu, del nu u mu. One more term. So this term comes when this del acts on this u. There will also be a term when this del acts on del u. That will be plus integral s lambda s mu u nu del lambda del nu u. Okay, and now we will reorder the derivatives in the last term, this one, and use commutator of covariant derivatives to get a Riemann tensor out, and things will assemble very nicely. So let's just write it out. So we get first of all you typed something wrong, let me just check. Yeah, I think I'm good. So this is integral s mu u nu. I'm writing the first term, del nu, s lambda del lambda u nu. So this hopefully is what term? It should be this term. So s mu is there, u oh, this term. No, this term is not this term.
That is
Okay.
an extra term which is 0, which has been added to make
Yeah, exactly. So what I've actually done is to take this derivative. So there's a few steps. It's very difficult standing at a board to read my own notes.
So the first term which was 0, instead of putting that as 0, if
I kept it.
You've kept that term, and then gives this. You take the u nu to the left over there in the first term. Take the u nu to the left.
Yeah.
And then you take the s lambda inside there.
Okay. Good. I'm glad you can see that.
And then combine it with the third term together.
But no, there was another term which was the SS term. Where is that gone? This is nightmare. This term, SS grad u, and then this is also SS u grad u, right? and I want written something wrong here. Okay, let me copy out what is in my notes, then you from a distance can tell me if it's right or not. This plus no, you know what's happening, and the reason I'm making a mistake is that I'm trying to read two equations at the same time. I think now I understand what's happening. Okay, up to here we are good. So S mu U nu, open bracket. Yeah, my eyes were just going to this next equation before I was finishing to write this one. No, I don't think I used that term which vanished. I think I threw it away. Okay, so let's see if you can agree with this. What have I done here? That term which vanished has vanished. This term I have rewritten as this plus this.
Okay.
And this term I claim should be the same as this, and now I know what I have done. I've used again this Lie derivative commutation. S gradient U is U gradient S. That's how I got this. That's what I was forgetting. So S lambda gradient lambda on U has turned into U nu gradient nu on S. The other terms are what they were before. And I've renamed some indices for convenience. Okay. Now the first two terms can combine. That's why I renamed the indices. And they will combine into S mu U mu del nu of S lambda del lambda U. This should be the sum of the first two terms. If it acts here, it's manifestly this term. If it acts there, it's that term. Good. And then there's only the Riemann curvature term, which, as you can imagine, will be important. So that term is just rewriting S lambda, S mu, U mu, R lambda, sigma, sigma. Good. And at this stage, I again use the Lie bracket thing to reverse this one back to U gradient S. Okay. So this is now equal to S mu U nu del nu U lambda del lambda S. Yes, beautiful. and actually I can take S as well as U common. Yeah, okay, this is better. This plus, so let's put a bracket here. This term has an S mu, so I'll write everything else that's not that. S lambda, U nu, U sigma, R lambda nu, U sigma. There you are. And now can you recognize what's inside the square bracket? Is it a familiar equation? The last term should give it away. Yeah, it's the geodesic deviation equation. Because whatever is multiplying S mu, that first line is d by is covariant derivative in tau squared on S. That's what the geodesic deviation does. Plus this term, and if you just check from your notes, you will see that in the notes it had a minus sign, but some of these indices were reversed. So it's this is the geodesic deviation operator, if you want to call it that way. So you can call this, and Wald actually does that, as S mu some operator S again. So you could call this mu lambda S lambda. Whether you can say this is the geodesic deviation operator in the sense that when it acts on S to give you 0, that's the geodesic deviation equation. However, we can't conclude that this is actually 0. Again, for the same reason, we have deviated to second order away from the geodesic. So this may be 0, it may not be 0, it may be many things, but we are just going to leave it like this. However, this is the answer for the second derivative in the total proper time, but only on the assumption that the first derivative vanished. Otherwise, there is a term which I had dropped, which I could bring back if I wanted, but it's just tedious. I took advantage of saying the first derivative vanishes to drop the mod u, assume that everything is affinely parameterized, and get this. Okay, good. So now, we have run out of time. I did not anticipate this happening. Okay, so then let me complete the proof tomorrow, and let me just state how we are going to go about it. So the theorem which we are going to prove, our theorem is equivalent to two statements. The theorem has an if and only if you remember. So A should imply B and B should also imply A, or A should imply B and not A should also imply not B. So I'm going to write two statements, and you can think about it, and tomorrow I'll complete the proof. If beta is a geodesic and it has no focal points, P and Q, then the proper time is maximized. And 2, if beta is either not a geodesic or it is a geodesic but with a intermediate focal point. Between P and Q. then T is not maximized. Okay. Now we have found a formula for dt by ds as well as d2t by dts. In one of these cases, supposing beta is not a geodesic, then dt by ds itself is not 0. If it is a geodesic, even with a focal point, then dt by ds is 0, and then I have to look at d2t by ds, which is that formula up there. And if it's a geodesic with no focal point, again I have to look at d2t by ds squared. So that's why I've set the stage to prove the formula. But it still takes a few, it will take at least 5 or 10 more minutes. So I think I better stop today and we'll complete the proof tomorrow. We'll also, however, bonus, we'll also state and prove Hawking's singularity theorem tomorrow, because it's a relatively simple consequence of focal points plus globally hyperbolic spacetime. And then we'll start on null, which as I promised is a whole different ballgame. Any questions?